Welcome back, Majors. This is part 4, or 3++ as we call it around here. This is even the finale, I'd reckon. Today's video, we're gonna go through and we're gonna figure out some common mistakes people make so that you don't make them. You could probably figure out the rest of the circuit, the rest of the PCB without this video, but a lot of people make the same mistakes, and I'm going to go over those mistakes. So if you want to avoid making them, save yourself some time and put your board's performance at risk, you don't want to do that. It's going to be quick. We got this. Let's go ahead and jump into the schematic. A great practice is to be organized. This is going to help you compartmentalize everything, make sure you make less mistakes in your schematic. The majority of times you make a mistake isn't actually in the circuit board. There's a lot of little tricks and checks in there that'll almost guarantee you don't make mistakes if you use the design rule checker. Most of your mistakes are going to come from your schematic. All the circuit boards I've had sent off to JLC PCB, the only time they have errors, it's always in the schematic. So a great thing to do is keep it organized. My favorite way to do that is to draw cute little grouping rectangles. That's not how you draw a rectangle. So go ahead, place a rectangle, place it around our transmitter. We're just going to organize this little unit as our transmitter circuit. We're going to do this for all the little kind of stuffs we make. Go ahead and put in some text. Call it our transmitter. Okay. Boop. And now it's compartmentalized. We're going to make more stuff as we go along here. That's just going to keep us organized. In fact, the next little box we're going to make is going to be for our connector. A lot of people make mistakes on the connector. It's got a specific pin out, right? We got specific pins coming from the processor part of your laser tag gun into here. So we got to make sure we get those pins right. Let's go ahead and place a symbol. We want to find connector 1x4. Connector 1x4, and this is going to be a socket. It's going to receive a plug from the motherboard. So you want connector 1x4 socket. Beautiful. We can go and place it down here. Why not? And our pinout is as follows. Pin 4 has our 3.3 volt line, so we can just copy that. Wired up. Pin 3 is going to have our receiver output, so we can label that RX. Wired up. Pin 2 will be our ground, so again, let's just steal this ground here. Make life easy. Wired up. And then our last pin will be our gate control. For simplicity, let's call that TX. And because we want these to be linked, right, gate control and TX, I'm actually going to get rid of the gate control label, and we'll just call it TX. We're going to control the transmitter with some pulse width modulation from the controller board, and it just goes right on that line. It controls the gate of the MOSFET. Perfect. Now let's go ahead and assign a footprint. Assign footprints. This is going to be a DuPont connector. DuPonts are great. They have this springy little fork on the inside of them that grab your standard circuit board pins. It is reversible, so you need to be careful with DuPont connectors, but they're still pretty handy. The most common size is 100 mils, silly error, which is 1/10 of an inch. So thank you, America, for using America units. It is in real life, or not in real life, whatever. It is 2.54 millimeters in metric. I might prefer one system of measurement. So we're going to open up our connector pin socket 2.54 millimeter group. And we want connector pin socket 2.54 1x4. Oh, vertical. We do not want an SMD variant. Let's go ahead and look at that footprint. That's perfect. This is what they carry in the shop. It'll fit just great. Let's assign it. Beautiful. Let's roll. And again, we're going to just make some cute little boxes to keep everything organized. So we go place, rectangle, line it up. Nice. And then copy some text down here. Name it connector. Oh, we are so happy. Wonderful. Makes my heart happy. Now the heart of our receiver circuit is our op amp. Let's go ahead and pull a symbol for him down. We are going to use the fantastical MCP-6002. 6002? No dash. MCP-6002. Here we have 4 options. So the 6002, the 2 designates that there's 2 op amps inside of here. So it's 1 chip, but he's got 2 op amps built into him, which is super neat because our circuit's going to have 2 op amps. Very convenient. We want the DIP package, the DIP 8. DIP stands for dual inline package. It doesn't give us a footprint, but we can assign a DIP 8 package. That's not too tricky. We can see here it has 3 units. So if we come down here, we see place all units, and we click OK. Make sure place all units is checked. Boop. We're actually going to click 3 times to put these all down. 1, 2, 3, right? I told you it has 2 op amps inside of it, and here's their nice symbols for the sake of convenience. And it also gives us like a power symbol. That way we don't have this attached to every single one of these op amps cluttering up our schematic. But this is the power for both of our op amps. They'll go on the same buses. Okay, lock and focus right here. What I'm about to explain is a little bit tricky. The step trips up a lot of people. In order to get the full swing of the AC input signal, we're going to have the center rail for the op amp where it's output, right? Do not make that ground. A lot of times in our LT Spice schematics, we make that ground, and then we have like a plus half voltage, minus half voltage. We're not going to do that here. That's going to make your life tricky and hard and sad. Your ground, we're going to make it the negative rail. Our positive is going to be attached to 3.3. We're going to have some filtering going on, probably, I'd guess, in your circuit. I don't know, not to spoil your fun or anything. That's probably what's going to happen. But that's going to be attached to that. So your middle ground will be your middle rail that your op amp default puts out to when there's no signal will be somewhere between 3.3 volts and ground. To make it super straightforward, sorry that might have been a little bit confusing, simply do not make the center rail of your op amps ground. Don't do it. You will cry. Now that we have this here, you can do this. That's the fun LT Spice part you designed and implemented on a breadboard. You know how to wire these up. I'm going to let you do that. But we are going to go to assign footprints to give it a footprint because it doesn't auto-magically come with one attached. We are friends, however, so I will find it for you. We want package DIP, dual inline pins, remember, very nice. We want the dash 8 because we have 8 pins. And I think we just want a simple one. 8-16 should do. Oh, no, that's so long. We don't want that. Not the 16, just the standard. There it is. There's our standard. Alphabetically janky. That's fine, though. Beautiful and perfect. We want them. So 62 here in package dips. Dip-8 W7. Happy little guy. Let's assign him. Now, let's talk photodiode. In the super standard symbol library, if we search photodiode, we get some pretty cute looking guys, don't you think? We could go online and find the exact model. However, I'm really nice, and I looked through all of the Kicad libraries, and turns out they already have it. Huge win, guys. BPW34. Remember, you have almost never the need to make your own footprints. You can do it. You can edit them a little bit. 99% of them already exist. In another video, we might talk about how to get them off DigiKey or another website, but Kicad has almost all of them. It's so nice. So here we have it. And it comes with a footprint. Mazel tov. Place that puppy. We are laughing. This next step is optional, but free and easy, so I highly recommend it. It's going to make your life very easy later if you choose to follow it. We're going to place down a connector in parallel with our photodiode. So go ahead and whip out a 1x2 socket, put them below, wire the anode to one end, the cathode to other, and now you have a socket in parallel. Now later when you do like the custom project in 390, if you wanted to add more sensors to your gun, or like a sensor to a hat or a vest, that way you have more than just the one sensor on the gun, all you have to do is wire single diode in parallel. Plug it in right there. Highly recommend doing this. If you decide not to do it, it will literally cost you nothing, and there is no downside. I said we're going to use a JST connector, so let's go to Assign Footprints. The JST connector is my favorite connector of all time. We're going to scroll down to Connector, JST, Alphabet. My favorite one is the one the shop carries most often. It has a 2mm spacing. It's called the PH. I believe we want the B2B. Yep, this is what it looks like. It's a through-hole connector. Makes soldering nice and easy. So in JST, it's number 113. JST PH B2B PHK 1x2. Great little connector. Let's go ahead and assign that footprint to our 1x2 socket. Apply. Okay. So good. Now before I let you loose to attack your circuit board with a vengeance, there's one more change we're going to make to our transmitter circuit. One of the tests is to measure the current that goes through your transmitter circuit, through your LED. To do that, you need to be able to break the connection and wire multimeter in series. That's the official way to do this test. There's other ways to kind of do it, but this is a good way to do it, and it's not hard. So what we're going to do is we're going to place a symbol, and we're going to place a connector that is a 1x2 pin. Perfect. And it's just going to go in series here. So we can pop out our power supply. And now just rewire. Perfect. Now when we're going to put a little hat, that's just going to bridge these two pins together. It's a little bit you can buy in the shop. He sits on top of these two pins and connects them whenever your circuit's not being tested. But whenever you want to test it, you just pop the little hat off and hook up a multimeter probe to each side, and you're testing current. That's super happy. As usual, let's go in and assign the footprint. A 1x2 pin. We're going to go to connector, pin header, 1x2, 2.54, or connector, pin header, 2.54. I don't know what I'm saying. And we're going to want the vertical. We don't want the SMD. Let's view the footprint. That's what it looks like. Perfect. Assign him. Apply. Okay. Great. That is our schematic all done for now. So let's go ahead and push these to the schematic via update PCB from schematic. When we click our update PCB button, we should see that we have no errors. That makes us happy. And we have all these new parts we got to put on our board. The only one here that has, like, you need to put this in a certain spot, right? We need to put the photodiode in a spot where it'll line up with the center little hole. So that way it can see and it's not blocked. Remember a cool gamer strategy. We're going to place down a rectangle from a corner. This one's going to be 16 tall, 17 wide. And we want to put it the diode center there. So let's get up close and personal. When we click M to move it, let's have our cursor in the center. That way it snaps to the center. We're happy. And go ahead and place it right there. Great. Now our board has two sides, a front and a back. The vast majority of the components we're putting on the front. However, we're going to want to put the LED and the photodiode on the back. That way you have like all of your electronics here on this side of your board, and then your LED and your photodiode poking out the other direction. We can do that here in Kicad. We can use the hotkey F to flip a component. Oh no, now it moved. If you rotate twice, it goes back. All right, flip, rotate twice. I'll be back in the same position. We're going to want to do the same thing to our LED, right? Currently it's locked. You have your selection filter down here. Make sure you have locked item selected if you're trying to select a locked item. Go ahead, click it, push L to unlock it, click F to flip it, and R2 times to rotate it back. You can tell it's been flipped onto the other side because it's little square here, this is called the courtyard, is now blue. You're not allowed to put parts within each other's courtyard, and he's on the back, so you're not allowed to, this is a back courtyard, it's blue. Great, we have both of these in the right position all lined up. Let's go ahead and lock them back down. Our other parts we can put pretty much wherever we want. It's going to be a balance of giving enough space to make sure you can solder well, also keep things dense. I'm going to put them like this, like this, like this. Ooh, no, I'll flip you. Yeah. See why I'm doing that? That way this hole's close, this hole's close. These holes are close. It's just a big game of Tetris, guys. Sweet. And then this guy in series with our photodiode. Do you guys see all this annoying, awful gray text? I hate it. It's the worst. It's useful sometimes. It doesn't actually show up on your board. The yellow text is the silk screen. That's what shows up on your board. This gray text are called, I believe, fabrication drawings, right? Yes, the fabrication drawings. When you send this, if you send this out to get built and assembled by a PCB guy, they like to see these so they can kind of judge your design and judge you a little bit, you know. Also make sure you're putting stuff in the right place, kind of a double check. We don't need it though, so we're getting rid of it. So here we can not see certain layers. We don't want to see the front fab or the back fab because it just gets in our way. So there it is, now it's gone. Now we're happy. Great. Now let's talk about copper planes. Your board is made out of 2 layers of copper. The front layer, which we see here in red, and is prefaced by the F, and the back layer prefaced by B, which is the blue layer. All of our parts intersect with the front and back layers because they're through hole. They punch all the way through the board. So they have a little bit of copper that's front and back on it. Everywhere that you see black, there is no copper. 2 layers is much better than 1 layer of copper because, like, you know, roads and overpasses, it allows you to have more complex connections. You can have intersections without the copper actually intersecting. Having multiple layers will allow us to create power planes. Power planes say, okay, everywhere there isn't a trace in this layer or a path, I will have this connected to a specific net. So, for example, all the piece on the top of our copper, that's not cut out to like become a trace, I will make it connected to the 3.3 volt net. And all the bottom piece, we can connect it to the ground net. This will make it so we need to draw less connections. There'll be less spaghetti traces everywhere. More importantly, it'll also help you reduce noise. You want clean signals for this project. That's how you get your grade. And that's also what makes your laser tag gun work. So we're going to have the cleanest signals in town. So we're going to draw 2 little rectangles, concentric rectangles. We'll delete them later. They just help us draw perfect rectangles and makes our stuff look nice. And then we're going to go to place, draw a filled zone, because we're going to fill a zone. Sweet. Copper zone properties. This is going to be on our front copper. We want it to be the 3.3 net. Perfect. So then we're going to click all of the corners to determine the bounds of that fill zone. And now if we push B, you'll see that fill up with the red thin layer. That's our front copper. If we zoom in on 3.3 volts, anywhere we should see that, we have these little attachments, meaning this is the 3.3 volt plane. Everywhere else remains isolated. That's how we create a power plane. Very, very helpful. Let's go ahead and do the same thing for the ground. Let's draw a filled zone. We want this one to be on the back copper this time. Ground, okay. And we click all of our corners. And we push B again, and that pushes the fill. So if we come into our ground, we see it's got its 2 little connection points. We are happy. We can look at our planes by toggling up here like who our active layer is between front and back. See, our back plane looks nice, front plane looks nice. Now let's get rid of these red rectangles. We don't really need them. We can use the selection filter. It's a good tool to do this and not highlight everything. We can go down and get rid of all items. We only want to select graphics, which are rectangles, and our zones remain perfect. Now we can go back to looking at all items. Maybe take locked items off that list. Now the final thing we're going to want to go over is our DRC, the Design Rules Checker. This is an automated checklist. It's going to go through a list of rules that are already programmed in. If we break any of these rules, it could mean our board has a connection or a manufacturing issue. It'll save you a lot of time. You really should do this or you're going to be sad. Let's go to run DRC. Uh-oh. Right off the bat, we got 4 errors. So our errors are missing connection between items. Now this is just because we haven't drawn it yet because we're still working on it. But imagine you were getting ready to ship this off to China to be manufactured and you forgot to connect stuff. Your board's going to get made, it's going to get all the way here, and you're going to have 5 useless pieces of copper because your stuff isn't connected. Not much of a circuit board now, is it? Life saver, the DRC. Good tool, use it. We can click on each of these, and it'll take us to the components. So that way we kind of know what it's talking about. So let's go ahead super fast and fix these by connecting our stuff. D to wired up. Perfect. Let's go to the next one. We fix that one. D to wired up. Next one. D to wired up. Now if we run our DRC again, clean, happy. It'll work. Good news. Now the DRC working does not mean that your board's guaranteed to work. It does mean that you have followed all of the connections and rules set by your schematic. So again, if you've made an error and your board doesn't work, it's probably because of something in your schematic. Now we still have a warning here. It says silk screen clipped by solder mask. So your silk screen is the yellow layer. That's the beautiful white text that shows up. Here the solder mask, or this pad, comes over it. So we can click on just the little letter, push M to move it, R to rotate it, and put it in a better spot. So you can move around all of your little letters as you please. Let's go ahead and run our DRC again. 0 errors, 0 warnings. Mazel tov. Let's send that puppy to China. Finally, what might be my all-time favorite feature in Kicad is the 3D viewer. You can go ahead and give it a click. It'll bring up a 3D image, ooh, of your board. Kicad has a 3D library of all your components too. They might not all be perfect, like that looks kind of tall, right? And it doesn't have the footprint for our photodiode. It just doesn't exist in its library. It's kind of a goofier part. But this is also a good sanity check to help your brain think, okay, is this going to fit good everywhere? Does this make sense? Is that the real part I want? It's a great little tool. It's also a good moment to take a second and pat yourself on the back and admire how pretty everything is. So get ready, good luck, buckle up for the rest of your design. Those filters aren't easy, but I hope you have fun. It's been a pleasure. Peace be the journey.